So once again, welcome back, and the chapter that we are looking at is about magnetism and matter. Okay, and today we are going to talk about the behavior of a magnetic dipole in a uniform magnetic field B. Okay. I am going to take a magnetic compass needle which looks like this: north side, south, or south here and north here, etc. This can be obtained by pivoting a small magnet, okay, a permanent magnet, and then imposing on that a foil, and there is a pivot, and on that pivot it can move. Okay, so this is a permanent magnet, okay, and it is in some magnetic field, and that magnetic field is uniform. Okay, the magnetic field is uniform. Magnetic field may be because of some instrument, and plus it can encompass the Earth's magnetic field over there. So we don't care how we get the magnetic field, but our magnetic field has to be uniform. Okay. Then in that magnetic field, the torque of the permanent magnet that it is, torque is equal to m cross b. Okay, where m is the magnetic dipole moment and b is the field. And of course, if given a choice, this is going to stay in the direction of the field. Okay, the needle is going to stay in the direction of the field, pointing north, etc. Okay, now from here the magnitude turns out to be equal to mb sine of theta, where theta is smaller. I emphasize, this is the cross product of two vectors. Theta is the smaller of the two angles that the second vector capital B here makes with the first vector m. This from the basic definition of a cross product, where a cross b is equal to vector c, and this vector c is perpendicular to both a and b. Okay. And the system has got a mass, this, that, but the property that we are going to be interested in, that the system has a moment of inertia I. Okay. So, as a result thereof, if we recall the definition of torque, then this is equal to the moment of inertia into d2 theta upon dt2, just like force is equal to mass into d2x upon dt2. Okay. This is equal to minus mb sine theta. This minus sign is indicative of the restoring torque. Okay, not the deflecting torque, but the restoring torque. Okay. So if theta is small in radians, tends to 0, then of course we say that sine theta is approximately equal to theta. This approximation we have talked about before. So now what I get is a beautiful equation: d2 theta upon dt2 is equal to minus mb upon I theta. M is the constant, b is the constant, I is the constant. All of them are positive constant, so I can write it in terms of omega square into theta. And this is basically an equation where the second order derivative of a function is proportional to the function itself. The derivative second order derivative is proportional to the function itself, and this is the basic definition of simple harmonic motion. Okay. So omega square, from here by comparison you can see that omega is equal to under root of mb upon I. Omega is equal to 2 pi nu, where nu is the frequency, and it is the inverse of capital T. So I can write that nu is equal to 1 upon 2 pi this, okay, and therefore T is equal to 2 pi and the reverse of it under root I upon mb. Okay. So from this equation, if I know other things associated with that magnet, so the magnetic field I can calculate as 4 pi square I, the moment of inertia divided by the dipole moment associated with the system. This is one thing. Now this is just similar to what we had when we had dipole in the electric dipole in a uniform electric field. So that is the kind of a thing which you have to recall and make this thing. Now another thing that we did with the dipole in the case of the electric field, the electric dipole vector, okay, was to understand the electric potential energy. And here, by comparison, we are going to talk about magnetic potential energy associated with our dipole, and we call it UM. I can call it any name, okay? For example, Sangeeta, no problem. But we should understand, we should be able to communicate to our teachers that this is like this. So UM is equal to integral torque as a function of theta into d theta. Okay. So I just write it. mb sine theta d theta. Poor m, poor b, they will come out. And integral sine theta d theta is turned out to be equal to minus cos of theta. This you should remember. Okay, that's not my problem, that's your problem. If you don't remember, it's your problem. So this is equal to minus m dot b. Okay. The dot product of the two vectors m and b is associated with the magnetic potential energy of the system. Now, I have not taken any limits over here, but whenever we have been talking about potential and potential energy, etc., we have been having a choice as to what will be the zero. So we take the choice, our choice, all people take this choice, you will take this choice, that when the angle, that theta, is pi by 2, then um is equal to 0. This is our choice. Okay, so let's see. In that case, if I have, okay, minus m dot b, let's calculate. At 0 radians or 0 degree that we have, will be equal to minus mb cos of 0, and cos of 0 is equal to 1, so this is minus mb. Okay, and similarly we have at pi, which is 180 degrees. This cos of 180 degrees is equal to minus 1, so this will turn out to be equal to plus mb. Okay. For example, I take it at 60 degrees, which corresponds to pi by 3. Um at this angle is equal to minus mb to half. Okay. Now this situation, 0 degree, that 40 angle, it is the most stable situation. Okay. And if you put it in this situation, 180 degrees, that is the most unstable situation. Now what I am going to do is as follows. Okay. As follows. I have it at any angle. Okay. Then I slightly disturb this angle. Let me see, because you can't see like this. Let me disturb it slightly by an angle. So what will happen? Simple harmonic oscillations will start. Okay, almost when the disturbance is very close to 0, then it is almost a straight line behavior. So it fits into the very definition of simple harmonic motion, and there are oscillations that are going to take place. Okay, and if we plot theta versus time, then we are going to get some kind of an equation, okay, where you can represent all things that you did in simple harmonic motion. Okay, we'll talk more about it shortly. So the next item that I must discuss with you is the comparison of the two dipoles, the magnetic dipole and the electric dipoles, put in the magnetic and electric fields respectively, and if we can remember formulae for one, we can derive the formulae for the other. But before that, let me just introduce a few examples. Here I have a permanent magnet with a defined value of m. The magnetic moment vector is 6.7 into 10 to the power of minus 2 ampere meter square, and the moment of inertia given as 7.5 into 10 to the power of minus 6 kilogram meter square. And then another information is it performs 10 complete oscillations in 6.7 seconds. This is like not touching it like this, but rather touching it like this. Okay. So anyway, they are asking what is the value of B, right? So this information gives us the value of T 6.7 upon 10, 0.67 seconds. Okay. And now if you remember, then the value of B is 4 pi I upon mt square. Okay. Of course, you can write the value of omega square is equal to etc., etc., and from that you can derive this formula. Okay, should be able to do that clearly. So this, when I substitute these values over here, okay, we find that the value of B is equal to 0.01 Tesla. Okay, the answer should always be written in Tesla, but sometimes they ask you to express the answer in Gauss. Okay, so 100 Gauss. Another exercise where we take a bar magnet with an M in a uniform B, and it makes an angle of 30 degrees with this. Okay, the value of the B is given as 800 Gauss, which I have to readily convert into Tesla, because we are doing MKs are the SI units, and therefore our unit should be Tesla. Torque is given at 0.016 Newton meter. Sometimes we also write it as meter Newton. Anyway, it's the same thing. It has got the dimensions of work. Okay, so they are asking us a question: what is the value of M? We'll calculate it here. Then they say that the bar magnet is replaced by a solenoid with an area of cross section equal to 2 into 10 to the power of minus 4 meter square, 1000 turns, and having the same M value which was obtained here, right? So you are asked what is the current through the solenoid. Okay. Easy questions. First part A, torque is equal to mv sin of theta. So I write m is equal to 0.0 m into the value of B into the sine theta, which is 30 degrees, is equal to sine of 30 degrees is equal to half, not 0.5. Always remember these values in figures like 1 by 2, 3 by 2, etc., etc. Okay, because you don't have a calculator to give the values, even though this value is very simple. So it turns out to be equal to 0.016, the value of the torque. So I can write M from this relation as 2 into 0.016 divided by 0.08, and this, when we calculate, it turns out to be equal to 0.4 ampere meter square. Okay. For the second one, although the value of m has to be taken as it is, but I write it the magnetic dipole moment of the solenoid. This is equal to number of turns n into the current into the area cross section. Okay. 1000 into I into 2 into 10 to the power minus 4 is equal to 0.4. So I can readily write it, because this will become 10 to the power of minus 1. So I write it 0.4 upon 2 into 10 to the power of minus 1. I take this here, becomes 4 divided by 2 amperes. So it's very simple. Other questions, if we are given the value of m and value of b. So often we ask how much work will be done if it is taken from this position to this position. Okay, so all we have to do is to calculate the value of u in the first position, the value of u in the second position, subtract it from the second position value to the first position value, and you will get the result. For example, if the situation is of the most stable state, from the most stable state we can rotate it to the most unstable state, which we call it most unstable, and we can say the least stable also sometimes, create confusion with the students. So here in the first case it will be equal to mv in cos of 0, that is equal to minus mb, okay, minus mb cos of 0, and then here 180 degrees, so minus mb cos of 180 degrees, which turns out to be equal to mb. So from minus mb to mb, when I come here, so this mb minus mb, that turns out to be equal to 2mb. So this kind of questions can always be asked, and you should practice many more questions in exercises that are given in your textbooks and health books. That will help you understand this more. So I now compare the two things. So to wind up this lecture, we are going to have a comparison of the magnetic dipole and the electrostatic dipole. That is, we are going to talk, because we are talking magnetism, so electrostatic analog. Else, if we are talking about electrostatics, we could talk about magnetic. So look here, on the left hand side I have electric field, and the analog is magnetic field, or the analog of the magnetic field is electrostatic field. The dipole we are talking about is m is equal to Ia or Nia. Okay, this can be also equal to Nia if number of turns is n. Nia, and A, always remember, is the area associated, and this is the surface area, so it is a kind of a vector, and m cap and a cap are in the same direction. So the counterpart or the analog is P is equal to Q into 2A into P cap. Okay, from negative charge to the positive charge in the system. Then the constants that we obtain, 1 upon 4 pi epsilon naught, okay, which I write as 1 upon 4 pi, 1 upon mu naught. Replace epsilon naught by 1 upon mu naught, and similarly we can replace mu naught by 1 upon epsilon naught, and we get mu naught upon 4 pi over here and 1 upon 4 pi epsilon naught over here. Okay. If we look at what is the value of the electric field in the equatorial direction, which is equatorial direction, which means on the broadside on position. Okay, then we find that the value is 1 upon 4 pi epsilon naught P upon R cube. And similarly, of course, in this case R is very, very large as compared to the A, where A is the distance between the two charges. Similarly, in the case of a magnet, a bar magnet, in the equatorial position of the bar magnet, the value of the magnetic field is equal to mu naught upon 4 pi m upon r cube. Very similar to that. Instead of 1 upon 4 pi epsilon naught, I write mu upon 4 pi, and instead of p, I write m and r cube are the same. Okay. On the axis of the dipole, which is the long side on position, we find that this value is 1 upon 4 pi epsilon naught, now 2p upon r cube, with the same conditions that are there. And similarly, on the axis of the magnet, the bar magnet, I find it as equal to mu naught upon 4 pi into 2m upon r cube. Okay. So there is a kind of similarity. There is kind of a analogous position between the electrostatic dipole and the magnetic dipole vector. Okay. So please bear in mind and make the comparisons, and you can write the various units if you like. Okay. Now, I top it up with a very simple and interesting question, and that is, there are two bars of iron. Okay. They look alike, and one of them is a magnet and the other is not a magnet. So how to say which one is the magnet? You have to pick up only one of the bars at a time. So look here, I'll tell you after that, but let us pick up this one. Okay, and either we have the end is north pole or the south pole. Okay, I bring it near to this end. Okay, if suppose this is not pole, then this end will become, it will be attracted towards it because this is not a magnet. Okay, here a south pole will develop temporarily, and if I bring it here, then here there is no pole, but a south pole will develop temporarily. So there will be a substantive attraction on this side and also on this side. If I keep it in the middle, okay, then also there will be an attraction, and the attraction will be substantive. Okay, but what if instead of taking this one, either this end or that end, you pick up the bar with no magnetism? Okay. Now, if you bring it near any of the sides near to this north pole, it will be attracted, and bring towards the south pole, there will be attraction, and the attraction will be substantive. Okay, with quite a vigor. But what if you bring this bar, okay, in the middle of it? So when we bring it in the middle of it, okay, now an interesting situation arises. That is, the strength of the magnetic field here is quite large, but just in the middle it is very poor. Not zero, but very poor. That means if this end or this end is brought over here, then the attraction will be very feeble. Okay. So now suppose I pick up this one, okay, and bring it in the middle here, then there is a substantive attraction, because we are already told that one of them is a magnet and the other is not a magnet. We don't know which one. So I will immediately say, if there is substantive amount of attraction between the two of them, I will say that the magnet is this one and this is not a magnet. If instead we pick it up, okay, and we if I pick it up, then there will be substantive. But if I pick this one, double tick, okay, and bring it over here, then the attraction will be feeble enough so that you can say in one go that the bar in my hand is not a magnet. So with that, similar kinds of very many things that are asked, so many questions are there which interest you, which test you, which not only test your knowledge, but they test your IQ, and you should apply your IQ, okay. And one of my friends who is no more now, okay, a very intelligent man, used to sometimes say in Hindustani that Shahid, Mr. Shahid, I have 4 names. People remember me with Syed, with Hasan, with Shahid, and also with Rizvi. And I have a surname also. I mean, alias also. Okay. So he used to say कि तुम्हारी समझ में नहीं आएगा, तुम्हारा आई टेढ़ा है, तुम्हारा आई टेढ़ा है और तुम्हारा क्यू पिचका हुआ है. Okay. So I टेढ़ा क्यू पिचका. But I hope that your I is strong and your Q is not pichka, and therefore you can always, if you understand and make a problem like that, do ask your friends as to what will be the answer to this kind of a, you don't ask them a question, but instead you make query. Okay? Query a word that is not created by the natural process, which was created by a person in a single day's time when he printed query and put more than 1,000 bills in the city where the query was started, and everybody started asking everybody else, what is query, what is query? And since then the query has also got the position of a question. Thank you very much. Okay.